Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for calculus students. It's a video where I'm going to take up one of the questions from the textbook on optimizing when using exponential and logarithmic functions. So the question is from page 321 in the textbook, and it's question 2a. And here's what the question says. It says, use the maximum and minimum algorithm to determine the absolute max and min values for the functions in question 1. So I've put the function here. So question 1 gave us this function and asked us to find max and min by graphing. And so this video I'm going to do question 2, which is to take the same function and to find the max and min using the algebra algorithm. So just to review, this is the algorithm for finding max and min through algebra. We need to find the derivative of the function and then find the critical values. And of course the critical values are the values where x, the values of x where the derivative is equal to 0, because that represents a turning point. And then once we find the critical values, we need to test the value of the original function for the ends of the interval and also any critical values that are in the interval. So let's go ahead and look at this question. So here's the function again. So it's obviously, we've got base e, so it's exponential. So the first thing we're going to do is we're going to take the derivative of this function. So there's a term here, subtract another term. So I like the way it's set up. So I'm just going to jump in and do the derivative. So of course the first term is base e, and we know that the derivative of anything base e is exactly what you see times the derivative of whatever's in the exponent there. So the derivative of negative x is just -1, and so that's the derivative of the first part. And then I have minus, so now I'm going to do the derivative of the second part. So again, it's base e, so exactly what I see times the derivative of whatever's in the exponent. So the derivative of -3x is -3. So I'm just going to make that look a little nicer. So negative e to the negative x. This subtract will be multiplied by this -3 to make it +3 e to the -3x. So I've done the derivative, but obviously I want to do some algebra here so that I can do the next step, which will be to make it equal to 0 and solve. So in other words, that's generally where you want to be factoring and simplifying. So what I'm going to do, and you may not need to see this, but I'm going to write it anyway, is I'm going to take the e to the -3 that's over here, and I'm going to rewrite it like this, just so that everyone is very clear as to what's going on. So we know that if we multiply two bases together, we could add the exponents. Well, I'm just doing the exact opposite. I'm separating the multiplication of bases into two different bases multiplied together. Sorry, same base obviously. And then that way I can clearly see what I can do in terms of common factoring. So that's what I'm going to do next. I'm going to common factor e to the -x, but I'm actually going to common factor the negative with it because we don't like our leading term to have negative. So I'm going to factor negative e to the -x from both terms. So of course the first term, that's exactly what it is. So the first term would just be 1. And then I need minus here because I factored a negative and there wasn't a negative. So then I need 3, and now this e to the -2x would remain. And again, it's always a good idea, especially with complicated or new algebra, to pause here and double check. If I were to multiply, would I go back to this step? So I would have negative e to the -x, and then I would have positive 3, and I would have e to the -x minus 2x, which is -3x. So that's my derivative. So now that I have my derivative and it's in a form that I can work with, I'm now going to do the next step, which I'm going to make it equal to 0 so that I can find critical values. Oops, negative e to the -x. And this is one of the reasons why we talk so much throughout this course about not just taking the derivative, but algebraically manipulating your derivative, especially doing common factoring. Because now I have two distinct things multiplied together, both of which, when multiplied together, equal 0. And that tells me that either the first thing would equal 0, or the second piece would equal 0. And that's where I could find my critical values. So obviously when I look here, it's impossible for any base to have an exponent where the whole entire expression is equal to 0. So there's no solutions based on that particular part of it. But if I go over here, it looks like I'll be able to solve. So I'm going to subtract 1 from both sides. Give myself a little more room. I'm going to divide both sides by -3. And because x is in the exponent, I don't want it there anymore. So how do I get rid of it? Well, because it's base e, if I take the ln of both sides, so what ln e does is the ln, which is log base e, basically just cancels out the e. So I'm left with negative 2x equals ln 1/3. And then divide by negative 2. So I'm just going to write it like this, which of course you could rewrite using properties of logs. You could rewrite this as ln 1 minus ln 3 over negative 2, or even better, we don't like negatives in the bottom, so if I transfer that negative to sort of the numerator, then I would have positive ln 3 and negative ln 1. So I'm just writing this because it's important that you see that, especially when you get into university, you're going to want to get used to not having to jump into decimals. But for our purposes, I'm perfectly fine saying that that's about 0.55. So now I have, that's a critical value, and there's only one. So when x is 0.55, there's a critical value. So now, if we go back to the original statement, actually I'll go to the next. So this function has a critical value at 0.55. That means that either 0, 10, or 0.55 represent where the maximums and minimums of the function are. And so now I just have to do those tests. So f at 0, so it was e to the negative x minus 3, nope, like that, minus, let me get back here, e to the negative 3 times x. So e to the 0 is 1 minus 1. 1 minus 1 is 0. So that's the value when x is 0. So now I'm going to sub in that critical value we found. So doing this math in your calculator, you should get about 0.39 roughly. And then when I test the other interval endpoint, which is 10, and punch that into my calculator, I get an incredibly small number, 0.0000. I think that's the right number, 0 is 5. So therefore, where are the maximums and minimums? So obviously we have a minimum of 0, and it occurs at x equals 0. And we have a maximum of approximately 0.39, and that occurs at x equals 0.55. So that is, again, the concepts here are all concepts that we've seen before, where we have a function, we're taking the derivative to find critical values, and then we're testing any critical value in the interval plus the endpoints of the interval to find minimum and maximum. So really the only addition to what we've seen in the past is that the function now has exponential and logarithmic calculus to deal with. Hope it was helpful. Bye.